Okay, I think we should begin. Are there any questions from last time? Exploration algorithms, a lot of fun. Okay, so this lecture is several different smaller lectures. Each of them I think is pretty interesting in its own way, but they're interesting in very different ways. The first part is on non-stationary policy evaluation. Okay, so what I mean by that is once you have exploration algorithms, you would like to be able to evaluate the quality of those exploration algorithms on the pre-existing data, right? So the fundamental way that an exploration algorithm is different from a stationary policy is that an exploration algorithm has a changing state. So the thing that you've learned over time is changing. That's true even with epsilon greedy, because the greedy part of epsilon greedy is learning as you get more and more information.
But not with uniform.
What's that?
Not with a uniform policy.
Yeah, if it's uniform, then yeah, it's easy. But if it's not uniform, then
yeah.
Anything that's actually learning in an online fashion suddenly becomes radically more difficult to evaluate. But it turns out we can do something which is somewhat effective. Okay, so we're thinking about contextual bandits again. And we still need to think about what learning means. Learning means minimizing our regret, or competing with a large policy class. I've seen that before. Okay, so now let's think about a very simplistic approach to simulating what happens in an online setting offline with exploration data. So we're going to think about a function.
I'm sorry, what are you trying to do?
We want to do non-stationary policy evaluation.
Okay. You want to evaluate a policy given some exploration history using a non-stationary exploration policy.
Yeah, so we're going to think about non-stationary policies. So these are policies taking into account of history.
Okay.
Or, I mean, implicitly, maybe they do updates in an online fashion, right? So the policy we want to evaluate is this policy pi. By the way, on Zoom, can you see my mouse?
Can I what?
See my mouse?
Yeah.
Okay. So we have a non-stationary policy pi. And then we have a bunch of exploration events. So last Monday, when we were playing around with different exploration algorithms, the reason why it was easy to evaluate them was because we had supervised data.
What is T?
T is the number of events.
Okay, so it's
Not
state, action, reward, and probability.
Yeah.
It's a sum.
Except I would not use the word state for the features because it's overloaded a lot.
Okay.
Okay, so last time when we were playing around with evaluating different exploration algorithms, the reason why that was easy is because we had fully supervised information that we're using to provide the feedback. Here we only have the exploration information. And now the question is, can we actually say anything about the value of the policy? So we're going to start with an empty history, and we're going to start with no recorded reward. And then for each event, we're going to check to see if the policy with the history chooses the action. And then with some probability, this is a parameter called pmin here. With probability pmin over p, we're going to add the event to the history. And then we're going to record the reward. So let's think about what this means a little bit. So then at the end, we're just going to record sort of the average reward over the history, or report the average reward. So why does this make sense? Well, does anybody see why it makes sense? So suppose that there were two actions, and so P-min, and let's say that we actually had really good exploration information, right? So then P would be 0.5, right? And then p min would also be 0.5. It would be the smallest probability. So we would be, whenever the random action agrees with the policy, we would add it to the history and record the reward. So for about half the events, they would go into the history. Right? And so what you can prove is that for all history links, for all non-stationary policies pi, for all, if the world is IID, so every event is independent, the probability of a simulated history of some length t is going to be the probability of the same history of length t in the real world.
What's the distinction here between world D and the real world?
Between what?
World D and the real world.
So we're thinking about suppose the real world is in fact IID. So every event that you get experience from is drawn from an IID process.
Okay.
So that's not true often in practice, but it's somewhat close to true. At least sometimes.
So what is in the real world?
The reward is just
The real world.
in the real world.
Yeah, the real world. Sure.
Okay, so in the real world, I think often you have non-stationarity, right? So if we think back to the MSN application of the contextual bandits, the set of news stories which is available changes over time. People's preferences change over time, and so you lose identical. You also have some loss of independence in the sense that a user who comes back may behave differently than a fresh user. Right? But these are there's sort of an approximation limit where IID makes sense here. If every user is different, well, the way I behave in response is probably not very related to the way you behave in response. And if we're looking at a relatively small time window, non-stationary effects aren't very much into play, and then the approximation of IID starts to make some reasonable amount of sense. Okay, so now one question is, why do you have this p min here?
Is it p min by p or should it be pi? Oh, the pi is not.
We're thinking of the pi as just being deterministic here, or at least we're only assuming black box access to it.
Trying to approximate something in some way.
Yeah, so you need the p min, but it's not an approximation. This theorem, if you can imagine how the proof goes, it's kind of a dynamic program where you say, oh, I have all the probabilities right up to this time, and then I'll have all the probabilities at the next time step, and the next time step, and the next time step.
Are we going to go over the proof?
What's that?
Are we going over the proof?
No. It's a lot of details that aren't very informative. It just says that we're perfectly simulating the same thing, what would happen in the real world. So why do we have the p min? So suppose that our data collection policy was not uniform. Suppose our data collection policy was the probability of 0.1 takes action 1, probability of 0.9 takes action 2. And then suppose that our policy sometimes takes action 1, sometimes takes action 2. So if so p here is either 0.1 or 0.9. If p min was okay, so there's already a problem because it says with probability p min over p. So then you need p min to be smaller than the smallest p, or else the probability would become larger than 1. But I think there's a more fundamental issue here, which is that when p min becomes small, you start with a history of length t, and then for the simulated length, it decreases according to p min. So at p min 0.5, you're going to have a simulated history of length t over 2. when p-min becomes 0.1, it's going to be similar length of,
Or the P will
of
change.
t over 10.
The P will continuously change because your exploration policy is.
P is changing constantly, but the p-min is kind of the probability, minimum probability that you encounter.
I mean, the P min can also change. That one will be constant across the.
Can't actually change if you want this theorem to hold.
I mean, if I'm collecting events using say epsilon greedy, decaying the epsilon time, it's going to change.
Yeah, so that's kind of an issue there.
So it only allows non-stationary evaluation, but the events have to be from a stationary policy.
Doesn't have to be stationary; it just has to obey a p-min.
Obey what?
It needs to have some minimum probability. So it can be non-stationary. It just needs to impose a minimum probability.
It has to be fixed, not fixed p-min.
Yeah. So let's suppose we take away the probability for a minute. So we just say, oh, we're going to take every event where the policy agrees with the chosen action and throw it into the history. Right? So that's kind of a straightforward, simple thing to do. And the claim would be that this can go pretty wrong. So let's think about that 0.1, 0.9 case. So when the policy happens to agree with a 0.9 action, it will tend to end up in the history. While when it agrees with the 0.1 action, it will tend to not end up in the history. And so in the history that we record, the 0.9 probability action will be much more prevalent than the 0.1 probability action. Even if the policy that we're trying to evaluate maybe would choose the 0.1 probability action half the time and 0.9 probability action half the time. So this is clearly very bad because we want something which works for every policy. And so the policy could just look into its history and see if there's a statistical violation of the fraction of the 0.1 probability action versus the 0.9 probability action and do something crazy based upon a deviation.
But how is this different? I mean, why would this not happen here? So because this if number 2 is nested under the if, right? If then.
Yeah.
So you only go for this.
So you only go when there's an agreement.
Yeah.
And you still rejection sample on top of that. And it's a rejection sampling which fixes that. Because when P is 0.9, 0.1 over 0.9 is relatively small until you'll accept those events relatively rarely. On the other hand, when P is 0.1, P-min over P will be 1 until you accept those events every time.
But because it's the end, you're just averaging. It's going to be exactly the same. In this like really generous case, because you're averaging over age, and age is increasing every time by 1.
It's not increasing every time. It's the increase. The then here, adding to the history and to the reward happens only if you pass the rejection sample step.
It cannot increase.
What?
It cannot increase.
It will stay the same.
Yeah, it will stay the same.
Yeah. So,
in order of expectation will be d times p min by d.
Okay, so
Sir, I have a question.
Yeah.
So, what's the difference if we include like XAR tuple, or rather we reweigh the R as like the inverse of the probability that we selected to put in the history? Like, what if we just say put every tuple like say R, but like take R prime, which is P by P min, so that in expectation we have, but it's like, is that the case where the non-stationarity comes in? Like in a stationary one, I would just reweigh the R and put it into the history, right?
So that's right. The history doesn't matter in the stationary case, right? Because the policy doesn't even depend upon the history in the stationary case.
Yeah. So, like, what is the return R by size of history in this case?
So here we're just predicting the average performance of the non-stationary policy.
Non-stationary. Okay. Okay, makes sense. Thank you.
Okay, but I think you are saying something which is on the next slide.
Okay.
Right? So this is kind of the simplest version of what a non-stationary evaluator would look like. it's very inefficient in the sense that it rejects far too many samples. And so you end up getting a very good sense of what an exploration policy would do with only a few samples, which is not necessarily that interesting because when you're exploring, you start out performing fairly badly. All right, so here is a master evaluator. This is a much more complex one, but it's not crazy complex, and you can still see the structure of the rejection sampling in the system. There's some more tricks going into the system, which I think which help in various ways. Right, so one trick is that we're going to look at the probability that the policy chooses an action rather than just assuming a deterministic policy. So you take the ratio of the probability to the recorded probability of the action, right? You use that for importance weighting. So 1 and 2 are being used to form a double robust reward evaluator, which will be unbiased. So that's where the R over C is output at the end. And then the rejection sampling here is there's a tweak to it. Essentially, how do I describe this? So there's some constant C, which we're using to, it's like that p-min, but we're allowing some violations of correctness. Right, so you could set C to be p-min, and then this would work fine. But that would be a little bit too conservative. You might be able to set C to be p-min over pi, right? And then that would actually make the probability be exactly 1. But even that is still pretty conservative. And so sometimes you want to set C so that you have maybe some 1% of your events have some sort of violation.
What is the semantics of Q?
Q is your set of previous sampling probabilities, basically.
It's reciprocal.
Reciprocal of that, yeah. So you're just keeping track of the ratios of the probability that your policy that you're evaluating does to the policy in the real world to the policy that you're trying to evaluate. And then you can look at some quantile of that to set C.
But the idea is to like go below p and by p, essentially.
Yeah, so it's kind of like a controlled bias introduction.
We can go in, but there is some W robust which corrects for it.
The double robust estimator is always fine. What this does not, I mean, this can make it so that this theorem here, this precise theorem does not apply anymore. But it's kind of a very controlled way to make the theorem not apply. And in practice, it's going to allow you to get away with using an order of magnitude more events.
So we could still use a simple, instead of like using W robust, we could use some simpler estimator and still apply it.
Yeah, you could do something simpler too. That's right. So there's a paper we have on this. Empirically, this is an order of magnitude better for non-stationary policy evaluation. But we were using this in the real world, and we still found it inadequate. So we came up with one more trick, which we had not fully analyzed. But nevertheless, I wanted to show it to you because I think it's kind of cool. So we're going to have a reward estimator. We're using probability ratios rather than indicator functions. We're using double robust. So we're trying to get a good reward estimator. And now we're going to do a rejection sampling, but it's going to look, we're going to do a combination of rejection sampling and importance weighting, basically. So when pi over p is less than 1, we do rejection sampling. And when it's greater than 1, we use an importance weighting on the sample. So empirically, this works very well. But in terms of the theory, we haven't really worked it out. The idea here is that, okay, so obviously you want to use as many events as possible. setting C to 1, which is what this is equivalent to doing, means you're using as many events as possible. But that means it would mean that the probability of accepting is perhaps too large in many cases. So we want to express the fact that this event is much more common than it might otherwise be. And so we use that with do that with an importance weight, which is greater than 1. So I think that there's some assumption about what an importance weight means for a learning algorithm, which makes this a valid approach to take. But we need to pin that down in more detail. Anyway, there's you can use explore eval in BW to play around with this. And then you can also use multiplier to set a constant C if you want. So are there questions about this?
How many samples does this use compared to the previous two?
I mean, this tends to use something pretty within some small constant factor of t. So it uses a large fraction of samples.
I mean, everything is small constant. I mean,
sorry, large constant fraction. Let's say
like
it depends on
percentage, in like 80%.
I mean, everything's going to depend upon how often you're in case 2. So in case 3, you never throw it away. In case 2, you're going to throw it away some of the time. And the question is, how often are you in case 3 or in case 2?
I mean, if you have a binary case, I mean, let's say p min is 1.5, and the first algorithm is already like using 50% of the samples. No, actually, it will use all of the samples in that case.
No, it only uses half the samples if you go here, because agreement is only occurring half the time.
Yeah. So that's 50%. How many? I mean, do you have like numbers or?
So how much better is this?
Yeah.
So here we're taking into account the probability of the policy we're trying to evaluate. So if the policy we're trying to evaluate is in fact 50-50 uniform random, we take every single event. Right, so I call this idempotent evaluation. If you want to evaluate a policy against its own data, you can use all the data. Okay, so there's a bibliography here. The slides are up on the website. Let's go to the next thing. Let's talk about the decision service. So this is a paper which has a large number of authors. And this is getting at making contextual bandits useful for everyone. Okay, so you recall that when I was first talking about things, I was saying that the fundamental reason for a lot of people why you want to think about this is that the y-axis is kind of funky in a lot of applications. So error into the precision recall curve has some relationship to the probability that somebody will click on a chosen ad, but its relationship is not at all clear. And it'd be nice if the y-axis was about, the actual probability of a click. Okay, so in practice, people are very blind. And so you would like to, I mean, people are very blind about, when they're just trying to optimize area in the precision recall curve, people are very blind about what they're trying to actually do. So you would like to try to do some sort of contextual bandit thing, right? So you have many examples of this where you observe features, you choose a news article, you observe click or not, and your goal is to maximize maybe the fraction of clicks. We can come up with many other applications like which landing page is better, or when should you reboot a machine. These are actual applications where people are actually doing things right now. Maybe which character from an EEG is the one that I mean to type when I think with my head.
What's an EEG?
What's that?
What's EEG?
Electroencephalograph. So it's a bunch of electrodes you stick on your head, right?
Okay.
And then you can measure things. You can measure brainwaves to some extent, but you can also maybe measure muscle twitches.
Oh yeah, the one you mentioned.
Yeah. So you can actually try to decode what people want to say using these kinds of things. So anyway, what I'm trying to say is there's a lot of different classes of problems where you really want to be able to do online learning. And yeah.
What is when should you reboot? Like what goes in there?
Yeah, so this is something that we're working on internally. So there's Microsoft has this cloud system called Azure, and they run a bunch of virtual machines in Azure, and sometimes the machines become unresponsive. So when do you restart the machine? When do you reboot the entire physical machine? These are the kinds of questions where context is probably fairly important. There's a cost associated with the decision to not reboot and the cost associated with the decision to reboot. Maybe if you don't reboot, the virtual machine will recover. Maybe not. And so the question is, when should your reboot decision come into play? The first one is which landing page. So I think that when you click on an ad, you go somewhere on the internet, and now the question is what should be there. And now maybe there's several options available. Maybe some are better or worse than others. You would like to be able to optimize that to something useful, or at least companies would like to be able to optimize that.
Is that the same as a homepage, landing page?
Yeah. Yeah. Okay. I mean, a homepage I think is usually used to describe a person's. It's a personal thing. But a landing page, what I mean is, where do you go when you click on an ad? Right? Mm-hmm. Maybe it's a car ad, and maybe there are different brands of cars that the advertisement could be referring to. So then you could swap in different choices of the car, and you could see what leads to more engagement. Okay, so there's a lot of possibilities, and I guess the common thing is they're all contextual bandits. So now the question is, how do we make it so that it's easy to actually use a contextual bandit in practice? So I'm going to tell you a little bit of history of the research, which I think we've discussed a little bit in the past, but I think 95 was the first time there was any contextual bandit paper. This is actually, it's a very impressive paper. We haven't gone into detail because it's computationally intractable, but this is the EXP4 algorithm is in this paper. This is actually working with contextual bandits in an adversarial setting rather than an IID setting, so it's also very impressive in that sense. There's work on reducing to supervised learning, which is what we covered 2 Mondays ago. There was the epic greedy, which is we talked about last Monday a little bit. There's kind of a drive towards computational and statistical optimality, which we talked about with the cover algorithm. There's nonstationary policy evaluation, which we just talked about. And then we have this deployable form of the decision service, which is out now.
So this is started with ABC.
Yeah, so I gave this talk at Facebook, and they said, you forgot some letters from the alphabet.
Picking some. You need to hire more people than ever start.
Yeah. All right, so now I think the question is, if you're trying to create a system for deploying contextual bandits, well, first of all, why is this even an issue? Because people are used to doing supervised learning, and they're used to, there's some challenges with deploying supervised learning, but they're not that significant in comparison.
What kind of challenges, like system challenges?
Yeah, so the question is what can go wrong? So for supervised learning, I think that the kind of thing which can easily go wrong is maybe trying to do something in an interactive setting, and then the latency is just too large.
Why?
Yeah, maybe there's lots of reasons why latency can become too
I mean,
large.
supervised learning, I understand, it's like you train it once and then you just board it and then.
You just stick it somewhere and then you just hit it over and over again, right? And then that works reasonably well when the problem is pretty stationary and when you can get good editorial advice. I think it does not necessarily work that well when the problem is non-stationary or you cannot get good editorial advice.
Or you have to personalize.
It's when you cannot get good editorial advice, right? Okay. So there's a set of things you want to do. You want to do exploration, you want to log things, you want to learn from that, and you want to be able to deploy your learnings to generate better exploration information. And I guess over time, I've seen a lot of ways that things kind of go wrong. Sometimes there are different people who are doing different parts of this process. And they just don't like talking to each other. Often the logging goes wrong in practice. And this is killer. I mean, there've been a number of projects I've seen fail because of this kind of issue. So maybe there's a pipeline of decisions being made, and you tweak one in the middle of the pipeline, but people just log the final output. And now you don't know what the decision was in the middle of the pipeline, so you're not going to be able to effectively control. You lost that information. Maybe you actually log the choice, but you did not log the probability of the random choice. And then your ability to do offline evaluation is lost. Now, I think this is actually fairly common. A lot of people know now that you need to be doing some exploration to get the right information to learn. And so the first thing that people do is they just go and add some randomization into the system, and they start getting some more diverse information. And that is useful. But being able to actually change the y-axis is another step beyond that, which is super useful. It seems like kind of a shame to not gather the information necessary to do that when you're already doing what's necessary to do it. Often the features are not logged until you log like a reference to a database, and that database changes over time, so that if you go and you look into the database later, it's no longer going to be consistent with what was seen online. Often there are issues with the runtime not being compatible with machine learning. So I've seen an example where essentially the pseudo-random numbers that people were using to randomly draw were not secure enough. They were not strong enough, which is very difficult to debug because things just don't work right. And the only way we ended up debugging it in the end was, okay, can we actually predict the action that will occur? Luckily, they were doing uniform random at the time. So the question was just, so the theory was they're going to do uniform random exploration. They used a pseudo-random number to do the draw. So what we did is we built a multi-class classifier to predict what the random action would be. And it turned out that this multi-class classifier had a non-trivial edge. It could actually predict the action with reasonably high probability. So that was an instance where somehow the probabilities were getting into the features because of the way the pseudo-random number was generated. It was using something from the features as the seed for the pseudo-random number. And it wasn't secure enough, so you could actually predict fairly well.
Why would you want to do that?
It was convenient, I don't know.
People use time.
There's lots of choices. In the decision service that I'm talking about right here, there's a notion of the seed that you want to use, and you feed in that seed. So if you have an event ID, that will be the seed. And if you want to do it based upon a user, then you use a user ID, that will be the seed, and so forth. Okay, so yeah, we made this decision service. You can either work with a client library or a web API. You send in context, it gets out a decision. The exploration happens internally, so we don't have developers screwing up pseudo-random numbers. Later on, the reward is reported with whatever the ID is for that event. So you have this feature, here's the features, here's the action, here's the probability of the action, and here's a join key. And then when the reward comes in, you have here's a reward and here's a join key type of events. So these go into a join server. The join server logs information basically. So it's going to, so you take in these different streams. You have the event stream and you have the outcome stream. And then for every event, you declare an experimental unit duration. You say, oh, I'm going to wait 10 minutes for a click or something like that. And then the join server kind of joins these, but with a 10-minute delay between the streams, so that it can take all the outcomes for an event and add them into that event. And then you can create these a more cooked version where you have the features, the action, the probability of the action, and a reward, right? So that goes into an online learning system, which is in fact VW. And then that system checkpoints the model periodically, which allows you to deploy a policy, right? And that policy can be deployed into the client library, which allows you to have sub-millisecond latencies, or it can go to the web API, and then you have to pay for the network time to the web API. But the advantage of the web API, of course, is that it's kind of more cross-platform than the library. Oh, and then there's one more step, which is that you can do all the offline and learning tricks that we just showed. All right, so the logs are available. All right, so let me, let's go here. Oops, is that what I want? This is what I want. Works. So if you go to aka.ms/mwt, there is a button, Deploy to Azure. You can click on that, and you can say, oh, okay, so some terms and whatnot. You can say Deploy to Azure. I don't want to see random things, so say cancel. And then if you don't have an account, you have to actually log in. But if you do have an account, then it auto logs you in. Okay, so it's creating a little form. Okay, so then you say, oh, I'm going to have a set of resources. So I'll call this John test 3. And then you can feed flags for VW essentially in to how you want that actual training to occur. There's some amount of initial exploration which happens before there's any events to feed into VW, and you need to declare what that is. You declare what the experimental unit duration is in seconds, so it's 10 seconds by default, but you can do 10 minutes or anything up to like 6 or 7 days. You can estimate the bandwidth required. These are all basically defaults unless you're doing something with an incredibly large amount of traffic. You can specify how often you checkpoint the model and update it. And then you need to input some sort of email. And then you say, okay, I agree to the terms and conditions. And then you say deploy. So I think that the cost of this baseline deployment is something like $100 a month. And it handles any reasonable amount of traffic. It's personal scale. If you need to go to many events per second, then you might want to think about doing something with a more expensive deployment. So this takes about 15 to 20 minutes to deploy. And then once it deploys, my browser's iffy. Once it deploys, you can start, there's a test drive that you can play around with. Let's get rid of this. Let's try that again. I don't know. There's a test drive.
This didn't get the blue screen.
And when your browser works, you can actually test it. Oh, we need to log in. All right, so I'll deal with that later. So you can log in. There's a little test drive. You can check to see that it's working, and you will actually see it doing online learning on the scale of 10 seconds.
How do you design the, like, what's the context, what's the decision?
So you basically have, there's some pre-cooked thing, which is what the test drive is. But you are free to choose what the context is. And essentially,
if I were to use this thing, where would I design the CDP?
Where would you design?
The contextual bandit process. I mean, how would I define the context decision?
So that's kind of your responsibility. This is a tool which allows you to run contextual bandits in production at scale. And it's exactly how you want to define the features, how you want to define the reward is all up to you.
Okay, I was just ask, like, I mean, you showed us the path. I mean, at what point do you define, like, where do you define the front end?
So essentially, there's I mean, the default web API has a URL that you hit. So if we go back to this, let me take a look at this. So there's an auto-generated random name, which is part of the URL that you hit when you want to send in the features and get back in action.
And can I take like any website and just like connect it somehow to this backend now?
Yes. So you can certainly connect any website to the backend. It works with JSON.
Okay.
So it's pretty convenient to do from a website. There's a bit more going on, and I'll get to that in a minute. Okay, so deployable contextual bandits. We actually did deploy this on MSN, and I think I mentioned this previously, but there's a lot of users. There's about a 5-minute model update frequency. It made a substantial difference in how many clicks there were and whatnot. People are very happy with that. Okay, and then I think the important thing is sort of, what does the system help you do, which would otherwise kill you when you try to use contextual bandits, right? So, okay, so one thing is, there's a lot of people I think who have tried to do online learning, and I've heard a lot of fail stories informally. You don't hear about them very much, but they actually do happen. So people who try to do online learning, they don't take into account these biasing effects that contextual bandits take into account, and then the system fails. So it's a very common observation. There's an issue with data lifecycle support. So it's very easy to mislog things, basically. And that mislogging is, I think, very killer in practice. Often the features are not quite the same as they would be in production, and then you kind of think that you have something useful, but you're not sure. And then that I'm not sure part is pretty killer as far as actually making things work. Another element which I think is very important is reproducibility, and this is not natural in a distributed system. So if you have a distributed system, by default, you do not get reproducibility. And I guess I think of reproducibility is sort of necessary for debuggability. So if you want to be able to debug when something goes wrong, you need to be able to reproduce what's going on online in an offline setting. So that's very important, and that's been very useful several times. And then online learning itself in non-stationary settings seems to be very critical to getting good performance. So if you go and you look at that paper that I mentioned earlier with ABC and so forth authors, we did a bunch of experiments where we looked at what happened if you used a policy that was a day old, and the performance went down a lot. 2 days old, down even more. 3 days old, you might as well not be doing anything, basically. Okay, so there's a deployable decision service. If you go here, that's kind of the root of documentation. And there's the paper, which talks about creating the deployable decision service. Everything is kind of open source. The algorithms are in VW, as we've discussed previously. The system itself that deploys into your Azure account is also open source. And then there have been other things that we've been working on since. So there's JavaScript interface now. There's a hosted version of the decision service. So that would be running in Microsoft's account rather than your account. And that means that you don't have to, it means you have less control, but then you also have less responsibility, basically, right? And then there's also an integration with cognitive services. So at Microsoft, cognitive services are typically a bunch of pre-canned supervised learning models, which do a bunch of useful things like entity linking or object detection or speech recognition. So you can feed these things in various feature channels into the decision service. It will hit these backends and then use what comes out of them as features for the actual decision making. So are there questions about this?
Yeah, I mean, there are student discount.
What's that?
Is there a student discount?
So again, the deploying to your own account thing is like $100 a month. It's not terribly high.
We have so much money in Azure, we don't know how to.
Okay, so here you have a great discount.
Anybody wants money in Azure, just ask.
You have a discount. For the host decision service, actually things are completely free right now.
I mean, Azure is has a Windows backend, right? I mean, you can't use Ubuntu, right?
You can use Ubuntu. So everything in Azure is basically virtual machines in the end, and there's plenty of Linux virtual machines going on. Okay, so now we're going to talk about something different again. Let's talk about contextual decision processes. Okay, so when you're thinking about reinforcement learning, there's a huge difference between, and that, by the way, here I mean real reinforcement learning, where you actually have a long sequence of actions and then you get a reward. There's a big difference between what happens in practice and what happens in theory. So in practice, people they're doing, deep reinforcement learning is now a thing, where people do some powerful modeling, but they use very simplistic exploration. They use epsilon greedy type things. In theory, if you're just looking at a Markov decision process, then there are very sophisticated exploration algorithms that work to get, and they're actually exponentially better than simple things like epsilon greedy. So they're enormously advantageous, but these don't actually get used in practice. And another question is, how do you actually address that gap? I think the fundamental gap, as we've been talking about over and over again, is that these things in theory don't deal with context. They don't deal with competing with a policy class. So we need a theory of reinforcement learning which deals with context and deals with policy classes. So that's what this is about. How do we make a theory of reinforcement learning that deals with context and with policy classes? Okay, so let's define something simple. That's a contextual decision process. This is very similar to looking to contextual bandits, except we have this horizon H, which goes from 1 to big H. So we're going to think of this as an episodic version of reinforcement learning. And now your reward can be dependent upon the history as well as everything else.
That's a difference from Markov decision process.
Yeah, so I'm not defining a Markov decision process here. I'm talking about contextual decision process.
So it depends on the history. That's the difference.
Yes.
Or the transition actions also depend upon the history.
Yeah, the history includes the actions.
Okay, so no Markovian assumption.
There's no Markovian assumption explicitly. Now, we're going to make an assumption later on. But right now, it's just you see features, you take an action, you get a reward. And that reward can be dependent upon all the stuff in the past. And then just that repeats over and over again until you get to big H.
So MDP can be seen as a special case of CDP.
MDPs are a special case, yeah. Okay, so now we want to compete with a policy class. That's actually going to be a little bit tricky. Instead, we're going to compete with a value function class. So given any set of features in action, we can get some sort of value. And now, given that you have a value function, you implicitly have a policy class, which is taking an argmax with respect to the action of the predicted value. Okay, so you can immediately run into bad news. It's easy to create a Markov decision process where, by the way, who knows what a Markov decision process is? Not everyone. Okay, so let me describe this briefly. So in a Markov decision process, you have a state which you observe. You take an action, and then your next state is drawn from a distribution over possible next states given the state and the action. Right? And so it's a very simple way of describing kind of a stochastic and otherwise Newtonian world where you know perfectly where you are, and then you have some distribution over your next steps dependent upon your action. And now your reward is going to be dependent upon the state or the state action, definitions vary, that you take. So you have a sequence of state actions that you take, and you get to pick up a reward each time, and then the goal is to kind of maximize the rewards. Right? So that's similar to this, except you have a state that you observe rather than just arbitrary features. And you're assuming that conditioned on the state, you don't need to know anything else about the history.
So H equals 2 or 1?
No, H could be, H could still be large, because some states, let's say there's a state which always gives you reward 1. And you would really like to get to that state and then just take the reward 1 over and over and over again. Right, so the reward, since the reward can be dependent upon the state summarizes the history. You should think of H here as being S.
I think there's like some overloading between a for loop variable for episodes and the history as in state action.
Yeah. Yeah.
I think,
Okay, so the claim is that if you don't bound the set of states in a Markov decision process, then it's easy to come up with a system where finding an epsilon optimal policy requires experience exponential in the horizon. And that's very intuitive, because you can, let's suppose that we have a bandit where each action is identified with a number. Then you could have you could think about a sequence of binary actions which spell out the actual number for that final action, and then you only observe reward at the end, right? So this is a way to kind of embed a bandit into a Markov decision process, where the number of arms can be exponential in the horizon, and then the amount of exploration that you need to do to succeed is exponential in the horizon, and then everything just falls apart in practice, right? And in general, if you have a set of policies, well, that will constrain things, but still, being dependent upon the number of policies is not good, because the number of possible decision trees or the number of possible linear predictors is enormously large.
what do you mean by required trajectories? You mean like exploration?
Yeah, so if you want to get an epsilon optimal policy, you have to kind of hit this many trajectories.
Using which exploration policy?
any exploration policy. So this is a lower bound.
Essentially useless.
Yeah, so this is useless. Okay, so what this means is that you need to have some notion of few states, right? And I haven't defined states here, so I'm going to have to define that later. Okay, so here's an algorithm. We'll talk about an algorithm first. And it claims this algorithm actually does good things in a natural setting. This algorithm is called Olive. Okay, so you start with a set of value functions. Oh, and let me tell you in advance, this algorithm is good statistically, but it's not good computationally. So this is similar to the setting that we were in 1995 when contextual bandits, when the first contextual bandit algorithms really came out. Okay, so we have a set of value functions. We're at the first time step, one of these value functions will be the most optimistic. And so we're just going to pick that value function, and we're going to roll out with that value function several times, right? So you can, because you have a value function, you also have the policy implied by that value function, which takes the argmax action according to that value function. Is that clear? I feel like I might be going too fast. Let's go back here. So given an F, you always have the policy which just chooses the argmax over the actions of the value in the features.
Value, right?
What's that?
F is a Q value, right?
We're just thinking of F as an arbitrary function. I don't want to attach a semantics to it. So Q value has a pretty strong semantics in reinforcement learning land. So many of these functions, F, will be terrible in practice. And so you want to find the one good one in this very large set of policies, or in a set of value functions. But yes, in an MVP case, it would be something like a Q value for particular functions. Okay, so from an F, you have a policy, taking the argmax. So let's move forward. If we have a policy, then we can roll out. We can start at h equals 1, roll out to big H, and then we can get a reward for that trace. Okay, we can repeat this several times because the world may not be deterministic, it may be stochastic. And then we can check to see if the predictions that F is making, if the value that F is giving is actually good. If the value that F is giving is good, then because it was the most optimistic F, we're just going to return that F and we'll be done. And so maybe F says, oh, the value you'll get is 1 at the first time step. And then it says 1 again and 1 again and 1 again. And indeed, when you get to the end, you see reward 1. And there's no other rewards in the way.
When F has a semantics, you're just trying to predict the reward that you will get once taking an action in the state for a given feature.
Yeah. Well, we're interpreting it that way, right? So F has no natural semantics, but we're seeking an F which has that semantics. Okay, so you have the predicted value, which is what F outputs. You have the observed value, which is what you actually observe when you do the rollouts. If these agree, because we had the most optimistic F, then we can just output that one and then we're done. Typically, they will not agree, at least at the beginning. So then what happens is there'll be you have this sequence of H steps going from the beginning to the end. You'll find that one step where there's the biggest disagreement between the sum of rewards realized in the future and what's predicted. Right. So then you'll roll out with F to that one time step. You'll act randomly across that time step in a contextual bandit style. So it's just epsilon greedy here. Oh, it's not even epsilon greedy. It's just uniform exploration. And then you'll act according to F after that. Right, so you roll out with F, you act randomly, then you roll out with F to the end. And then you're going to collect rewards for these traces which have a deviation at that bad time step. And then you can eliminate every function which has a large Bellman error. And I'll describe what that is in a moment. Okay, so the way this algorithm works is you start with a very large policy of a set of functions. And when you're in this else clause, you're going to eliminate things which behave poorly, which give you bad predictions. And then that set of functions is just going to get smaller and smaller and smaller over time. And now the question is, how many samples are required to find a good F?
How do you define the notion of large disagreement?
Yeah, so this is going to use large deviation bounds all over the place. Okay, so one question is, what is Bellman error? So let's suppose you, for any policy, pi, you roll out h minus 1 time steps with that policy. So you use this policy h minus 1 times. And then at time step h, you act according to f. So a sub h and a sub h plus 1 are going to be drawn according to pi sub f. And now you have the prediction for the value when you take action A from observation X. You have the realized reward at time step H, and then you have the predicted value at the next time step. And in expectation, the value of this is supposed to be 0 if you have a good value function estimator. So the Bellman error is how much this disagrees from 0. And we'll be able to test for that statistically to see if an F is statistically different from the one which would achieve expectation 0.
Why? So this is the self-consistency equation written in a form.
Yeah.
If this is 0, it just only means that F is satisfies a self-consistency equation. It doesn't mean F is optimal.
That is true. And actually, when I say optimal is sufficient but not necessary to achieve this self-consistency. So self-consistency, what we're really going to require, this is a good observation. We could say, I require that the optimal F be in a set of our family of Fs. And that would be a pretty strong assumption. But really all that's required is that a self-consistent F be in our family of Fs, which is the weaker assumption.
Sure.
Okay, so here's the theorem. The claim is for all contextual decision processes, for all Fs containing a self-consistent F star. Okay, so now there's this Bellman rank, which I'll define in a moment. If you have Bellman rank B, with probability 1 minus delta, the number of samples required is just B squared horizon cubed, number of actions, log number of functions, divided by delta, all that divided by epsilon squared. Okay, so that's, this is the first, well, this in the paper which is immediately prior to this, at the last NIPS, are the first papers which give you a guarantee like this, where you have a logarithmic dependence upon the number of functions in a real reinforcement learning setting. Okay, so we have one more step, which is, what is this Bellman rank thing? And then we'll be done with this. Okay, so we have this notion of the Bellman error, which is dependent upon, so you roll in with a policy for h minus 1 time steps, and then you act according to F twice, and you see how consistent F is in predicting the reward, essentially. Right, so the difference in F in expectation between the h and h+1 time step should be equal to the expected reward. Okay, so this is your Bellman error, and now we're going to define a matrix which essentially uses pi in one dimension and uses the f in the other dimension. And so this is a ginormous matrix you would never actually write out. But nevertheless, we can think about it, and then we can say, oh, what is the rank of that matrix? And that's the Bellman rank. And now the question is this actually a useful thing? Because, you know, there's some giant matrix you have little intuition about, and you talk about the rank of that, which is even kind of hard to think about. And the claim is this is actually a useful thing. So the claim is that the Bellman rank is essentially bounded by the number of states in settings where you think about things. So if you think about Markov decision processes, then the Bellman rank is bounded by the number of states. The number of states is greater than or equal to the Bellman rank. You can think about large state MDPs where there's sort of there's a bunch of states which are basically equivalent, and then you could try to define superstates which contain individual states because you have a bunch of. Okay, anyways, you can make new guarantees there. You can apply this to reactive POMDPs. So a POMDP is a partially observed Markov decision process, which is just saying that you don't actually observe the state, you just observe some observation from it. And now, as long as this can be solved by a policy which just operates on the features that you see at each time step, that's a reactive POMDP. And now we get good results. There's also PSRs, because it's a different reinforcement learning model. Linear quadratic regulators are a model from control theory, and there you get something which is kind of a known guarantee. So I guess the summary here is that the Bellman rank seems to summarize a lot of different notions of what a simple reinforcement learning problem is. And then the results that we get they actually work when you have a rich observation space, which is unlike, let's go back to the beginning. Unlike this E-cubed R-max algorithms.
I mean, is it right to say that intuitively a low Bellman rank means that the number of functions which have a 0 or close to 0 Bellman error are few? No. I think what happens is how many times do you have to repeat this loop to learn? And if you have a large Bellman rank, you may need to repeat this loop many times to learn. But if you have a small Bellman rank, not so many times. So lots of things are interdependent and they will get eliminated all at once.
Yeah. Yeah. Okay. So this is I would say is a far from complete theory of reinforcement learning. It's obviously not computationally tractable because you can't afford to enumerate policies. There's a lot of other issues people worry about, like world models and options and safety. These are all essentially unsolved problems in my mind. But I wanted to make sure that you're aware of them as well, because it's a good topic for research.
What is options?
Yeah, so the idea with an option is that instead of having a policy, instead of having a single function which describes how you should act given your observations, you have a set of functions, and you have a master function which can kind of fire up one of these sets of functions, use it for a while, and then come back to the master function. So think of it as a habit, right? So an option is a habit. Maybe walking down the street is you don't really think about where you're putting your feet. There's just kind of an option which is running, which drives you. right? And then you get to the end of the street and you're like, okay, now where do I go? So then you have to consciously think again. Right? So people have described options for a long time. Nobody really knows how to learn them in an effective fashion. It's well known that if you have the right options, then it kind of trivializes the problem of doing reinforcement learning. But finding that right set of options in a realistic way is a challenge. Safety is an issue where, you know, a lot of these exploration items don't take into account how severely bad an outcome could be. We wouldn't want our children to run into the street in order to discover what that is bad to get in front of a car. Right. So, but I mean, these algorithms do that, right? So there's clearly some issues.
What are world models?
So for world models, I mean, the fundamental claim is that in reinforcement learning, true reward signals, the reward signals you get from the environment, are actually very sparse compared to the complexity of what you need to learn. And so the question is, how do you actually get more information from the world in order to learn more effectively? And one thing you could try to do is you could try to build a simulator of the world internally, and then use that to guide your exploration and your learning process in a much more intentional fashion than otherwise is possible.
Well, what do you mean, like you built a model of reward function and transition?
And transition matrix. I think particularly the transition matrix.
I mean, one thing which kind of bothers me a bit about reinforcement learning is like the exploration policies that I generally see, like epsilon 280 or something, they're all local.
Yeah.
Like maybe there's like an action which takes you eventually to a state which is very rarely visited, but it won't be taken with that. It's going to be taken with the same probability as the remaining actions which all lead you to the same state. So you should be taking this rare action more, because after 5 steps will be in a much more rarer state than, so like all the exploration policies, they're like just focusing on the immediate randomization as opposed to long-term randomization.
Yeah. So the E-cubed and R-max algorithms are dealing with the long-term thing. This one is dealing with the long-term thing implicitly through this kind of seek and explore approach. But you're right that the ones that are used in practice tend to not have this behavior. All right. See you later. See you next week, Monday.